Then we got up to 1999, and something new happened, which made possible this absolute revolution that I'm going to explain about. So I had this idea that Chebotaev had put up that you could make a comb, but it's just a dream because we didn't have any components that would work with that. It's like building something out of an assembly of angels that are all on pinheads, right? It just, I don't have time to talk about it. It doesn't mean anything. But finally, as you'll see, something came out of a completely different field, and that made it all possible. So this special optical fiber is actually what that is, and that led to basically a revolution. So these nonlinear interactions then made it possible to measure the frequency, and our colleague in Germany had a paper in a certain date in April, and 14 days later in the next issue of the journal, our group had a paper. Ours, I thought, was an interesting one. It wasn't the first, but ours is the first one that did in a single step. So now we've got a box where radio frequency goes in, and it's maybe 100 million oscillations per second, and what comes out is light, where the frequency is 100 trillion oscillations per second. So I'm going to explain a little bit about how that happens. So this thing, anyway, is called optical comb. By end of 1 year, there was 20 papers in the world, and by 4 years later, this incredible, unexpected event happened in which the Nobel Prize Committee decided that this was really an important business, of course, for which I thank them. So here's a microscope picture of the end of a piece of fiber. Now, this was made at Bell Labs. Now they're called Lucent Labs. And what you see is the diameter here. That's 100 microns. That's about the same as a human hair. And we have in the center, then, there is a rod, and the light is focused into that. And around that are a bunch of holes. This was originally tubes. There was a rod, then a bunch of tubes around it, and then a sheath. And when you're done, it's stacked up, and it's just about this size. And then you take it to the lab where they make fibers, and they heat it and stretch it, and they give you back in a couple days 20 kilometers wrapped around and around, and it's very thin, just like the hair. So that was interesting fiber, and this young man, Janendra Renka, was ending his postdoc, and he wondered, what can I do that's dramatic? So I'll take some of this fiber and I'll put this really powerful laser that I just got and put it in. You may not be able to see the color so well, but it starts with red light coming in, and perhaps you can see that it changes to green and purple. So this was presented in almost midnight post-deadline session, and I saw this result, and I knew this is a comb. This light goes through here, and it's extremely short time. So this is all bright, and then it's quiet, and then it's bright again as these pulses are coming 100 million per second. So I realized that this was really a comb, and I realized that this is the start of a whole new epoch. But I've got to get some of this fiber. So I called up this guy, and please send us some fiber. Well, I can't do that. I have to ask. And so then he asked the manager, and the manager says, well, I have to ask. And finally goes to the lawyers, and the lawyers say, we've had this for a huge long time. Nobody has ever had a use for it, but you want it. Consequently, it's valuable. Consequently, we won't give it to you. So that was very disappointing. However, scientists, not fully respectful, so maybe he misunderstood. Anyway, I once, then 2 weeks or a month later, received an envelope, a normal business envelope, and it was marked as if a child had written the address on it, no return address. One stamp was enough to get this empty envelope to me. An empty envelope, this is weird, but a look inside in a bright light like this, oh, look at that, there's something in here. So then here is a foot of this magic fiber. Yes! And so we could try it. So this idea then of having pulses that are coming in and getting the comb out, it was possible even for us. And so again, here's another case where 15 people invented the equivalent kind of idea about how you compare this and get some of the technical details out. We were able to see these optical heterodyne signals that we needed. So going from this fiber then, we could broaden the spectrum by a huge factor. Here's our laser width, and here's how broad the spectrum is after the fiber, but you can see that with your eye. It's a whole bloody rainbow. Okay, so this is pretty nice stuff. And then with this, so we even call it magic rainbow fiber. But what I think is important is that after all this work, and you saw those labs with a huge big number of lasers in it, and here's how it is now. There's a microscope lens, you focus the light into this little fiber. This is 5 centimeters length, and it comes out the other side, and there's another lens that focuses the blue light coming out. And like, that's just what you'd like. And it could be even simpler because we can weld the fiber, a regular fiber, onto the end, send our light in fiber. So now the whole, even the laser is a fiber. Fiber to matching to nonlinear fiber, and finally there's white light coming out, and you're off and running. So I'm going to tell you then some applications of this. Let me just try to synthesize this. This first picture was 1960. We add on a few years to 1999, and what has happened is by the efforts of people that are interested in pulse lasers, we got shorter and shorter pulses, femtoseconds even, 10 to the minus 15 seconds. And by the efforts of the team in Boulder, we learned how to make these lasers be amazingly stable. And some other kind of people were interested in trying to see what's the limit that matter can handle. Let's put the most light in the smallest thing and see what happens. Well, it makes white light. And so this nonlinearity was possible, and that then led to this the existence of the comb. And it's 39 years after the first laser. Well, okay, that's an amazing kind of thing, but okay, so I need to say this was a fantastic collaboration between the group in Garching near Munich and us. But what the consequence of that is that this logical tightness of having pulse lasers and continuous wave lasers totally disappeared after we have the comb. The comb is there, the beam is on, you see it's always on, but if you looked in time with really high resolution, it isn't actually always on. It's on as a pulse, and then empty, and then another pulse. And in fact, the duty factor is only 1 in a million of its being on. So it makes it possible to have one light source, and on one side you talk about what its frequency is, and it's on the other side you talk about what's the line width. It's just absolutely transformative. And even the intellectual part of this takes some time. And when the first papers were given, and would make lectures in the audience, that somebody over there would say, "Now, Mr. Hall, you can't really have things that are sharp in frequency and sharp in time." Well, I'm sorry, sir. The actual fact is you can, but you need a pulse train, not a single pulse. So let me just try to say 2 more words about the comb itself. What to remember about it, it's frequencies that are separated equally. If we want to make it in the time domain out of waves, I've got 5 here, different colors, and they're all adding up, and I fixed it so they're all synchronized at one place. And if I ask about how much power is there, well, if there's 5 waves and each is 1, then altogether there'll be amplitude of 5. So that's pretty straightforward. But I didn't mention that the number of waves that we're adding is 1 million. So now if the amplitude is up by 1 million, the power is up by 1 million squared, trillion times. So I have a laser which is making some power like this little pointer does. You take a factor of 1 trillion on that, you have a light which is stronger than makes an electric field that's stronger than what holds glass together. So you're going to be writing tracks in the glass if you send it in that, or you're going to be able to make these measurements that I've been talking about. Of course, it's not on all the time. If you have it 1 million times shorter, 1 million times added, then it's 1 million times shorter. So the time domain is really a point. So its consequence is that you have a laser like this green pointer, and it's on all the time, but you know that it has these waves in it. And actually the waves don't last very long. They're only 2 femtoseconds. What is that? 2,000ths of a trillionth of a second. That's not much, but that's where visible light is. And if you instead look on a different time scale, 500,000, almost 1 million times slower, then this green light is always on, and you can now, with the laboratory instrument, you can begin to see that there's pulses. And so the pulses are thin, you can hardly resolve them. In fact, you can't resolve them, you just see it as an impulse. And if you compare that up with your other laser, then they kind of match up. So it's better to have the magnification 500,000 in here. So this impulse, when I look really tight in it, it's got this oscillating character. So that's lets us make frequency comparisons between this. And the result of that is that we can learn simply in a minute or some few minutes what used to take, I had a group of, at the biggest was 15, most of the time it was 12 people, and we have 5 years. That begins to get expensive. And here's something that you can come in with your fiber laser connector, screw it in, go get coffee, and come back, and the results are just printed. It's simply a breakthrough. Now let's talk about so I can insist on this. You maybe can already figure this out. If you have pulses in time, you get one language. If you have pulses in frequency, you have another language. So, and this was first understood by Hench and Chebotaev. What I've told you about is something that's just fully as valuable as this thing. Actually, on the trip here, I was so stupid that I had one of those things in my pocket, and they found it, so I need to buy another Swiss knife. Anyway, this tool is universal in a slightly different sense. It connects microwave frequencies and optical frequencies. It works like there's gears. Gears isn't quite the right language, but you saw those pulse lines there. So does it line up after 947 or line up after 948? That's the sense in which it's gears. And this is a completely realistic model for things. And one of the things which I passed over rather quickly, but one of the things of the future is that in order to have force and get jobs done, you're going to be working in groups because contributors have different knowledge bases. And so that's the case here. This guy, Thomas Udom, is a super good guy. He works in the group in Germany. This Scott Diddams is a super good guy and works in Boulder. And so I invested in United Airlines and sent Scott across to visit with them. So he had 3 trips over. Thomas Udom had from Germany to us a few trips by Lufthansa. And of course, it's the same airplane because they're cross-coded. But anyway, it's collaboration that made it possible to make this comb business possible. The collaboration continues. Here's a research meeting of our group in one of the research institutes of Munich, held with outdoors and with adequate kind of beverages. We entered when they opened in the afternoon, and they're finally turning the lights off when we go home. But notice this, that's the critical thing. Out of that is distilled on this napkin is the most beautiful equations and circuit diagrams and optical configurations. It's hugely valuable to interact with colleagues that have a different skill set or overlapping enough that you know the language. It's really a